Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my pleasure to introduce Olga Papa-Emanuel from Brown University. Olga she did her bachelor's in computer engineering and information systems at the University of Patras in Greece. She did her MSc from the University of Athens in the same area, and she's finishing up her PhD at Brown University. Her advisor is Ugur Sentintamel, and she's a Paris Kanellakis Fellow from Brown. And so today, her broad interests are in the area of data management and distributed systems. So again, it's my pleasure to welcome her, and she's going to get started with her talk right now.
Thank you. It's been a pleasure being here. So I'm here to describe how we can create extensible overlay networks to support stream processing and dissemination applications. So when I talk about streams, I refer to continuous flow of information. And this continuous flow of data can come from different sources depending on the application we're actually looking at. So for example, if we have applications that focus on environmental monitoring, then we have large-scale sensor networks that continuously send measurements to us. For example, what is the current temperature? If our application is used for online network games, then we have multiple players participate in these games, and they continuously send the new state, what is the weapons they hold, or the position in the game arena, for example. And applications that focus on information dissemination, where they continuously send updates on news articles or the content of various blogs. Systems that focus on monitoring. We want to see what is the network traffic that we have in the system. So we want to see what is the, for example, the IP of the sources that are trying to connect to our network, what is the destination of these connections, what are the protocols they're using, right? So in all of these applications, you can assume that we have a large number of sources that can generate these streams. And also we have a large number of users, or monitoring applications, as we call them. And, And what the users want to do is receive this information, or part of this. And what they do, they join the system and they provide their profiles or their queries. And these queries express which streams they want to receive and how they would like to see them processed. Okay? Now, the job of a middleware for supporting this type of applications is first to collect the information from the sources, process them, depending on what are the users' queries, and then disseminate the results to the end clients. Right? And in most of these applications, sources and clients, they're going to be highly distributed in the world, right? So centralized solutions that collect all the data in a single location and process it there, they're not going to scale. Instead, what we need is a distributed protocols and infrastructures, where we deploy a large number of servers that are placed in different locations in our network, okay? And then use protocols and algorithms that rely on localized state and localized information exchange. And now the easiest way to create a new network service today is to construct a new overlay structure. So overlay networks are actually virtual networks that are built on top of the existing IP infrastructure. So they are built on the application level and allows us to decide how these servers will communicate one with the other. Who will be my neighbor, for example, in this distributed infrastructure. And now having these servers placed in different locations allows sources and clients to just connect to the closest one and send their queries or send the data and get back the information that they wish. Now, apart from creating this overlay network, an important functionality that this middleware has to provide is finding the efficient routing paths, network paths, for streaming information from the sources to the clients. Okay? So we have two important functionalities that are common in all of these applications: construction of the overlay network and routing logic. Now, you can imagine that different applications also have diverse needs when it comes to their processing logic and their performance expectations. For example, if we're using this middleware to disseminate notifications for weather alerts, then you can imagine that our servers will probably have to evaluate simple predicates. So notify me when the temperature is greater than a specific threshold, right? So you can see this as doing processing on relational data. Now, if the middleware is used to disseminate RSS feeds, when an RSS feed is an XML-based format for syndicating news, then our servers have to deploy XML-based processing algorithms, right? So we have to process, for example, XPath or XQuery expressions and send XML documents, different processing logic. Let's look at the performance expectations. If the system is used to detect intrusion attempts in our network, then it is very important for us to get the results of our queries back as fast as possible. So latency is an issue, right? Instead, if the system is used for environmental monitoring and it runs in a peer-to-peer setting when everyone is contributing their resources, then fairness of how these resources are utilized is important. So we want to make sure that the bandwidth consumption is not greater for someone. It doesn't have big variance between the participants. And currently, the way these applications are supported is by providing specific solutions to support each one of these specific expectations. So for every application, we have to create this middleware from scratch, which means we have to search what are the right algorithms for creating these overlay networks. We have to implement them, test them, debug them. And then if we have to change something, we have to change the performance metric that we need to optimize for, then we have to do this process all over again. So this makes the development of these applications very difficult and time-consuming. And it makes it very hard to incorporate different performance metrics and different processing logic, right? So instead of providing very specific solutions to each one of these problems that I mentioned and many more others, our approach is to create a generic infrastructure that can support both stream processing and dissemination applications. And it can separate the application logic and application goals from the actual creation and plumbing of this middleware. So we designed this such an infrastructure that is extensible, which means it can be customized by different applications. And applications, the developers, they will provide certain specifications to the system. And given these specifications, as we will see, we will automatically build and periodically optimize the overlay structure for supporting these applications. Okay? So here's the outline of my talk. I hope I motivated why such a generic infrastructure would be a very useful tool for application development. And in the first part, I'm going to talk about how we can support extensible stream dissemination. We're just going to look at how we can route streams on this overlay network. And in the second part, I'm going to talk about how we extended this stream dissemination system export with stream processing capabilities and see how we can support distributed stream processing on top of that. So let's start with export. Export is a generic stream dissemination system, middleware, that creates a single tree, an overlay tree, that connects sources that want to publish information with clients that want to subscribe and collect this information. And of course, the published information is going to be routed on top of this overlay tree. And periodically, export uses an optimization framework that tries to adapt the structure of this overlay tree to the current network or workload conditions. So we're going to change, for example, the overlay links that we are using. So imagine the following problem. Having all of these servers participate in a complete graph, and our job is to figure out periodically which links of this graph we should use to construct this tree in order to address what is currently happening in my system. Okay? And the key characteristic of export is that it is extensible. It can express and can optimize different performance metrics, so and also can handle different profiles or query types and different data types that can be produced by the sources. So let's look at how the communication model in this system. So export relies on the publish-subscribe model for disseminating information from the sources to the clients. We start by constructing a spanning tree of our available nodes in the system. And whenever a client wants to participate in this middleware, simply connects to one of these nodes and sends its profile. For example, I want to receive notifications if the temperature is greater than 10. And these profiles are being propagated towards the root, and filters are being placed in intermediate locations inside the network. Okay? And as you can imagine, as more and more of these clients join the system, more and more of these profiles are being propagated and being stored. So we can optionally merge these filters and just keep the more generic expressions that we have to in order to figure out who wants what, right? And now, given this filter-based tree, we're going to selectively send data that the sources publish only to the interested clients. So whenever a data message comes to each one of these intermediate nodes, we will actually look at the content of this message, match it against the stored profiles that we have, and figure out if there are any downstream clients that might be interested in that. So in this case, this message is being sent only to the second client by using these filters. Okay? And I show you here an example that just uses relational data. You can imagine that this can be XPath or XQuery expressions, and this could actually be XML documents that have to be sent downstream, right? Now, the good thing about this publish-subscribe model is that it provides a loosely coupled architecture. So sources do not need to know where the clients are and what they actually want. And the same goes for the clients. They don't have to know who are their sources and when they're going to publish information. And this allows these systems to be highly scalable with a number of data publishers and data consumers they can support. And not only that, but they adapt very efficiently to changes in these subscriptions and unsubscriptions. So for example, if I have to change this profile now, I don't have to notify all the sources about changing this value from 10 to 20. I'm just going to push the change to my first client, and the change is going to incrementally be done inside the network. Okay? And so what export provides is actually an abstraction over this publish-subscribe model. So instead of focusing on specific ways of managing this data, of merging and matching this data, we provide an API to the application developers and ask from them to provide for us the implementation of two basic functions. One that tells us how we can merge two profiles. So given two profiles, how can we figure out a more generic expression to represent them? And how we can identify if an incoming message matches a profile that is being stored in one node. And if they give us that, we can handle their own data types. We don't rely on specific algorithms. So you can think of applications putting here and using their favorite algorithm for aggregating XPath queries, right? Or their favorite index for figuring out how relational profiles can match incoming data.
Binary OR?
Sorry?
Is merge just binary OR? Right? If you have profile 1, profile 2, it's just an OR, right? Versus something, am I missing something?
It's all about, you want to keep one expression, right? So you don't want to evaluate both of them. So if you can, it depends on where it comes from. So if it comes from, if I want to find out what my subtree wants, then it's actually going to be an AND, right? At this point, it's not going to be an OR.
So it's only, okay, no, I don't understand what it's doing. So you're propagating up the tree, the thing that says, I want to see everything that matches this expression, right? It's because you're going to have to propagate it to one or the other of both subtrees, right? So the subtrees push up to you expressions, and then you have to compute the
For every one of my direct children is an OR. But if I want to see what is going on one step later in this subtree, it's actually going to be an AND. So for these cases, it is an OR, you are right. So I have to see either this or this, and this is what I propagate. But what I propagate after, it's an AND, right? So it's going to be an OR or an OR for this node. And then whenever it sends its merge profile upstream, this has to, it's better if it is an AND, right?
So you have a merged profile, which would be temp is greater than 10 or temp is greater than 5, which of course is equivalent to temp.
So this node only has to know that down here is greater than 5. It doesn't need to know the greater than 10. This is what I mean.
Right. So
but in this node, it has to know greater than 10 or greater than 5.
Right. Okay. So you're doing some more sophisticated processing on the expressions to figure out how to flatten them into something smaller in a case like that where you can.
It's the application which does that. The application is the one which provides.
Yes, the application will actually tell us how we can if this, let me say, you are right, here it is an OR. When you propagate up, it's an AND. But the way we're actually going to do it, it depends on the application. We're not going to bother in providing the algorithm for that. So the application will give us, how to figure out this AND and OR. And there is a more extended yes?
What is the data model? I mean, these are all expressions, these are predicates on single tuples over a stream. Is that, what is?
So in this case, yes, it is simple. So you assume you have a tuple that comes with a specific set of attributes. You know the schema, and then when you express your queries, it have to be expressed on top of the schema. If it is XPath, it's a different. You follow the XML.
You can think of it as streaming.
Continuous flow of tuples that comes in, or continuous flow of XML documents, for example, RSS feeds. And there is a more extended API. This is not sufficient, but I'm not going to refer more in this talk about this. I can talk offline if yes.
Things drop into your network. What is the
Excuse me, they can drop?
What is the reliability? Does your network, do links break? What happens?
Yes, we have a very basic fault tolerance capability. When if you lose connection with your client, then you try to connect with your parent, then you try to reconnect with your grandparent. And if that doesn't work, then there is a registry outside the network where you can go and say which are the available nodes, and so I can actually connect and restructure this tree.
But as far as the application is concerned, it's a best effort semantics. So you get me as much data as you can.
It depends again on the application. So if throughput is your concern, yes, this network can be optimized so I can get to you as much data as I can. And we try to guarantee the semantics. So we try to make sure that, we do actually make sure that you don't lose any data. So inside every one of these nodes here, we're going to cache data and make sure that if someone loses this connection, it can go back and figure out what is the data that I missed while trying to reconnect in my network.
So how do you control this point tree creation? Is it like you have central server which does that? Or
the tree creation?
Yeah, like this is most interesting part of it.
Yes. So I'm going to talk about how we initially set up the tree, because the structure of the tree depends on the optimization.
It's practically per stream, right?
Excuse me, this per?
So the tree should be per stream, right? It's not like generic tree for everything, right? It's for every set of consumers, it's separate. You need different tree, right?
No, as long as you're sending the same, you don't need a different.
No, right, but I mean that you have single stream or like, I don't know, application, right? Set of streams.
Yes, RSS. So this can connect multiple RSS sources. So you can pull data from different sources. So it doesn't have to be one single. So I'm not going to create one tree just for the CNN, RSS feed and another for the ABC. It's going to be the same thing, and they're just going to be sent through the same tree. And the filters will help me, because when I want, imagine that I express queries like give me the articles that have the word, election. So I want.
Sources will be different. Like this is, I understand, because a source of CNN tree can be that node which is leaf node right now, right on the right on that tree, and sources for other can be connected.
You publish through the root. So you publish through one single location. So you're gonna get the data from there.
So if this location is remote to me and I have close location, I cannot publish for that.
You can publish by connecting to the root and just sending your data through that.
So always have to connect to the root.
Yes, and in the second part, we're going to see how I split that in multiple trees and actually have multiple roots. Next. Okay. So please ask me about the more extended API later. We're happy to talk about that. But I want to focus on this talk on how we can support different performance expectations. So, and we refer to this as cost extensibility. So what does it mean? We ask from the application developers to provide for us what are the characteristics of the overlay tree they wish to create. So what are the optimization metrics they want to see the system try to improve for, and what are the constraints that they have. And to assist them with this task, we provide a metric definition grammar, which allows them to combine different building statistics that our nodes collect with various aggregation functions. And this can help them express a variety of metrics statistics. And we were very careful when we created this, designed this grammar, and make sure that we can capture as many of these the metrics that people have used for evaluating these stream dissemination systems. So we can express bandwidth consumption, the load that a node has for simply forwarding data, what is the matching latency, time it takes me to identify if there is a match on the stored profiles, what is the bandwidth capacity of my system, how much data I can actually send through.
Talk about these metrics. Are you going to talk about them in more detail?
Yeah,
okay.
and how we define them. Okay. So how do we define this metric? We're going to use a two-step aggregation. In the first step, we're going to define the local cost of a single node in the system. And this is expressed as an aggregation of statistics we collect from the neighborhood of a node. So what is a neighborhood? We have two definitions of that. One is the nodes that collect a node to the root of the tree, and this allows us to capture path properties on top of this overlay structure. So we can express path latency by just summing the link latencies, right? Now, the second neighborhood is the direct children, and this allows us to capture relationships that exist between a parent and a child in this system. So for example, how much data I'm sending out depends on how much data I'm sending to each one of my children, or what is the overlap of the profiles between those with my children. I have to see the relationship, and use an algorithm for figuring that out, right? So once we define the cost of a single node, then we use another aggregation function to aggregate the cost of all the nodes in the system and express the global performance metric that I have, right? So let's look at an example. Let's assume I want to create a tree that minimizes the total bandwidth consumption while keeping the latency, the dissemination latency, under a specific threshold. I have to define optimization metric. So in our grammar, it would be expressed like that. Let's parse this. This part here expresses the outgoing rate of each node in my system, right? So to see how much data each one sends out, we have to sum how much my children are receiving from me. Great. So if I sum this over all the nodes in the system, then I have the total bandwidth consumption. The second step, the developer has to express what is the constraint metrics. So this is dissemination latency. This is a metric that is going to sum the link latencies of the path and see how much time it takes me, measure how much time it takes me to send data from the root to each one of the clients. Now, given these specifications, export will parse these definitions and figure out customized nodes to collect statistics from the proper neighbors. So for example, in this case, I'm going to collect the outgoing rate of each one of my links to my children. And in this case, I'm going to collect the latency to my parent and just measure the latency that connects me to my parent in this tree. Right. And using this aggregation, two-level aggregation step, we can express a variety of metrics. So we can express the maximum path latency, provide some quality of service, the bandwidth capacity, the minimum bandwidth bottleneck in the system, the processing load that I have, the total data that I have to send. So I'm probably sending some data that I'm not interested in just because I happen to be in the middle of this network. So I can measure that. Okay. So now the question is, how exactly we're going to optimize this metric? And our goal is to try to, yeah.
One more question, which is that I'm not seeing, how does time enter into your performance metrics? So in other words, the states of things may be different at different times. And are you minimizing over, the worst moment in all time, or are you? This
is an adaptive system. So what we do is that we continuously and iteratively have this process that runs in some period, every 2 minutes, or what, it depends on your system and how stable it is, and tries to see what are the statistics, the history of statistics I have collected. So based on that, try to figure out what is the change I should do to my network, what should be the best structure. So this is how it comes into. So we're looking at the history of a certain time and just try to project that in our structure.
So when you're doing min over a particular period of time that you.
When I'm doing min, I'm doing the min of all the costs over all the nodes, right? And then I try to improve that, maximize it if it is a min, right? So I have to maximize that based on what the statistics told me. Within that period of time, yes, they collected the statistics. So our approach is to try to change the structure of this network. So we're going to remove some links and add some links that are probably going to work better for us. And there are, of course, two main challenges. First, there is an exponential number of possible configurations of trees we have to evaluate, right? So this means that we need an efficient way of figuring out what is the impact of every modification we're going to do. And of course, we're going to measure that without having to apply the change in the network. And so instead of focusing in the whole network, our approach is to try to to create a localized protocol that just tries to improve certain optimization areas. So we divide the network in optimization units, as we call them. And here I show one. So an optimization unit has a specific height. In this case, has a height of 3. And every node in this tree is going to be responsible for its subtree that has a height of 3. And it's only going to try to optimize this specific area. It's going to be responsible only for that area. So different nodes have different optimization area, and they try to improve it locally. And now inside of each one of these areas, we will not try any arbitrary move, but instead we're going to limit ourselves to a specific set of transformation rules. And by limiting the moves we can do, we can control, first of all, how this system is changing. So this allows us to figure out which one is affected or not. And also, by keeping these modifications local, it reduces the overhead of this optimization because we reduce how many nodes we're going to affect every time we change one network link. Okay? So the question is, what are these transformations? Okay.
If you said it, I missed it, but how big do you expect these networks to be and how pushy? Are these 10 nodes or 1 billion? Or somewhere in between? Where? Yes. Somewhere
in between. Our experiments went up to 400 nodes in on Planet Lab. Okay. Yes. So what is the structure depends.
You're showing binary trees. Is it binary trees?
Well, because you cannot fit one in the slide, but it depends on your definition of the performance. So if you have a constraint on the fan out, if you have limited bandwidth, for example, outgoing bandwidth, then you're gonna impose some constraints on how many connections. Yes. So again, it will depend on the constraints you impose on these performance metrics.
But your system will allow sort of arbitrarily.
Yes, we're going to see later that we can have a star and everyone can connect. If you can handle that, if you have the infrastructure to handle that, it's great.
So if single root node cannot track multiple?
As I said, in this case, we assume just a single root, and then in the second part, I'm going to show you how we can handle multiple trees, and we're going to see that I have an operation that splits the streams that are going in one tree and just divides it in multiple ones. Okay. So what are these transformation rules we will apply? We provide 2 primitive transformations. That one is, moving one child one level lower, and moving a child one level higher in this optimization unit. And this is a complete set. It can move eventually the system from every configuration to any other tree structure. And for these primitive transformations, we have a cost model that allows us to figure out what will be the benefit we get from making this modification. Now we go one step further, and we have an extensible set of optimization rules. We ask applications to define for us composite rules, so they can take this child demotion and promotion and define a sequence of these transformations. So for example, instead of moving this tree one by one, I can actually have a whole subtree promotion. This allows the system to move much faster and improve much faster, and also helps us sometimes avoid getting stuck in a local optima, because making these small modifications, it's kind of dangerous, as we will see later. So, and now, which one of all of these units we will try really to optimize? Our goal is to improve the performance of the system. So we're just going to focus on the areas that can achieve this for us. Let's look at this metric. We try to minimize the maximum CPU load in the system. So we have one node, which we call the critical, and it's the one that is doing most of the processing now. We will only touch the optimization units that can change this node, that can touch this node and have an impact on the global performance. If we're trying to improve, for example, the average path latency, then we will touch all the optimization units, and because every improvement in every path would actually have an impact on the global cost. So inside of every one of these units, the owner, the root of the unit, will iteratively evaluate the impact of every transformation rule that we have defined and see what is the gain that we have in the global performance cost. And the best one of these transformation rules is going to be sent to the root of the tree, which is responsible of figuring out which one of these transformation rules on optimization units will give me the highest benefit. Okay? And of course, we have a way of parallelizing this process, because if you just try to do it one unit at a time, it's not going to get you far away. So we figure out which units they don't have overlap, so we try to parallelize them to improve them in parallel. And of course, we can figure out which transformation units they're not affecting, transformation rules, they're not affecting the same set of nodes, and trying also to resolve any conflicts and figure out if it is better to apply two transformations instead of one. Yes?
The merge and match operations that you mentioned are for you black boxes, right?
Yes.
So how can you reason about the CPU cost and all if it's a black box? How do I know whether...
Very good question, because I skipped that part. So what we allow application also to do is define for us the statistics we're going to collect. So if you want to measure the CPU latency, and that depends, of course, on the profile type you have, you can provide the function, the method that does this for me. So back, well, maybe I shouldn't really do that, but anyway. So yeah, I shouldn't. So here I'm just mentioning specific built-in metrics. We have a way of letting the application developer specify how we collect these statistics. So they can give us a function that says, here's how you measure CPU, and then you mention the node cost is this CPU, is what you get the result out of that, and the maximum is if you aggregate using the max function over all the nodes in the system. So the way you collect the statistics can also be extended. It doesn't have to be bound to these built-in statistics that we collect. Even these ones can be changed. So for example, you can say, yes, so if you don't like the way we measure the link latency, because we're sending 10 kilobytes on every link, and you want to use ping messages, you can actually do that. You can say, you can override our methods for collecting the statistics. So there's one thing missing. How exactly we're going to evaluate what is the impact of a transformation, right? And our approach is to try to figure out which nodes are going to be affected. And the aggregation functions that we used in the metric definitions can tell us that. So we define, first of all, what are the dependencies of a node. Let's assume this simple case. We have the cost of a node is defined as an aggregation over path. It could be the path latency. Now, if something changes on the path to the red node, everyone below will be affected. Their cost will also be changed. So these are called the dependence of this node. And based on that, we define the dependence of the whole unit. So this is the unit, and these are the dependents. These are the nodes that they lie outside this optimization area. Their network connections will not be affected if we do a modification here, but their cost changes might. So our goal, whenever we try to evaluate the gain, we have to look in what is going to happen inside this area and what's going to happen here. But as I said before, we want to keep our protocols localized as possible and the information as local as possible. So what we try to do is use the aggregation functions to summarize what is actually going to happen, what is the state inside this dependence. Keep the state local in these nodes here in the last level, and try locally to figure out how much we will affect someone outside my optimization area. So a very simple example, if we're using an additive, a sum, for example, to aggregate node costs, then we will have to sum what is the cost difference inside this, for every node inside this unit. Oh, sorry, excuse me. And we will also have to, we aggregate the costs of everyone here and try to see what is the incremental impact on them. So here's a very simple example. Let's assume I want to minimize the average path latency. And now the cost of the red node here is going to be 13, the sum of the link latencies. And we want to see how this change, which reduces its cost by 1, will affect the global performance. Now, everyone in the subtree will be affected equally, because this is an additive, the path latency is an additive aggregation over the path, right? Now, in export, we're not interested in intermediate results of our modifications. In other words, we don't want to find out what was the cost of every one of these nodes before or after the change. We just want to find out what is the aggregated impact on the global cost. And the only information we need for that is how many nodes we're affecting. So if we have that, if we know how many nodes we're affecting, we know by how much. So it's -1 for this and 3 times -1 for everyone in my dependence set. So -4 in total, right? Of course, you have to divide it because this is the average path latency. Yes?
To remove and add nodes.
To remove?
Yeah, because like if I want to optimize latency, probably I just will remove all nodes and just keep leaves, right?
But nodes might have clients attached to them. No, the assumption is that you don't remove nodes. You're just adding and removing overlay link.
Bootstrap the tree. Like initially, I have nothing, right? I have just a set of nodes which are not connected.
You connect only if you have, so you have a set of nodes that are not in the system, and suddenly they get one client attached to them. You connect to the registry and say, okay, I have to connect to this tree now and get some data. It tells you where the available nodes. You pick one, let's say randomly, initially, as your parent, and this is how you construct your tree. So if you participate in the system, it means you have a client. Otherwise, you wouldn't be in the system. And the assumption is that we don't move clients around. So everyone here has to remain in this tree to get the data to their clients. Is that clear? So you wouldn't connect unless you have...
Routing nodes. You just have nodes which have clients.
They act as routers because if you are here, you're not only serving your clients, you're serving someone else that is your subtree as well. So you act as a forwarding, but never as a only forwarding node. No. So we only need to maintain in this case how many dependents I have, which is one single value. Let's look at a different metric. If we're trying to maximize the bandwidth bottleneck in the system, how much data I want to send through. So what's the bandwidth bottleneck? Well, over my path, this is defined by the link that has the minimum capacity, right? So in this case, the minimum capacity is 4. So this is the cost of this node. It can set, let's say, 4 kilobytes per second. And now, again, we have to see if we change this, how much we're affecting our dependence. And we maintain 2 aggregated metrics. One is what is the cost, the aggregated cost of this dependence. So what is the minimum cost here? And what is the worst link that I actually have in this subtree. So in this case, it will be 5. This is the worst link that I have across among my dependents, right? And we make one modification. Now the cost of this node is reduced by -3. It's 1 because I introduced a worst link here. And I want to find out how much I'm affecting these nodes here. And so we have to simply evaluate these conditions. Let's look at what they mean. So this was the case before. And the first condition here says, if the dependence and the red node were sharing the same worst link before and after the modification, then the effect on these nodes will be the same as the effect and the impact on the red node, right? Now, if that was not the case, if they were not sharing the same bad link before, so again, it is 1 here. If that was not the case, if the dependence had a different worst link, it was not the same as 4. So now they have a worst link, which is 3. How much I'm affecting them? Well, the second equation and condition shows that. So now I move the bottleneck from, it was 3, now it is 1. They're actually sharing the same worst link. So all I have to see is what is the new cost of the red node? This will be the cost of everyone here, minus what was the difference before, which is 3. That was their worst link before. So the change that they will experience is going to be -1. The outcome here is that you simply need to evaluate these small conditions, right? And you only need one state to do all of this. You just need to know this aggregate value, GY, which is the worst link inside the subtree. Okay? That's the only thing you need to know. And this is because we know the semantics of the aggregation function. So using these semantics, we were able to categorize, without depending on the actual metric, what is the state that we have to maintain? And the good thing is that in most of the cases, it is of constant size, or it depends on the number of dependents that I have, the number of nodes I'm actually affecting. So this is and as you will see in the experiments, this is a very small state that we have to keep. And as I said, this state is independent of the actual metric and independent of the transformations that we're going to apply in the system. So this allows the system to be highly extensible. Yeah.
One high-level question here is that how robust is this cost model? In a sense, so the ones which just depend on counting of the number of children may be okay, but there may be others where you actually need to measure, say, how many bytes per second have I sent, or the latency between a certain pair of nodes. Mm-hmm. How stable or robust are those measures that you have found in practice? In practice,
it depends on when you're running things. If you're running it on Planet Lab, which I did, things they're not very stable there. But you can do a pretty good job. Things are not changing. You have to make sure that you keep a wide enough window to make sure that you're not affected by high, spike loads. You don't want to improve because suddenly one link is very loaded, because that is not going to reflect later in your system.
But in a sense, you could run into a system, into a state where you made a change very quickly based on some recently corrected statistics. You found that the new plan, the new tree, is worse. Then you kind of went back and oscillated back and forth. But do you have any proactive measures to
this can definitely, if we have. So first of all, we try to make sure that we don't make small changes that just slightly improve the performance of the system. So we have a threshold and say if you can achieve over that, then you can go ahead and do it. If we actually measure also the optimization overhead that we have in terms of how much data we're sending. So if you see that you're trying to improve bandwidth consumption and you are sending more data and you're not saving more data than what you're actually is going to cost you, then you're not going to do it. The assumption, however, here is that things are changing temporarily, so they're actually changing, so you try to adapt. You don't really want to not allow the system to improve at all. You want to adjust your statistics collection period according to what your system, how the system behaves, and not stop I don't think the solution is to not allow the optimization. The solution is to do a better job in collecting the statistics. And of course, in order to maintain this state, although small, we have to send around a lot of information. So that really can increase the overhead of the system. So we again use the aggregation functions to try to approximate some of the statistics. So if we have as I said, communication cost because of statistics. So what we try to do is look at the optimization definitions and try to see if some nodes have higher impact on the global performance. And for these nodes, we broadcast their statistics more frequently, making sure that everyone has updated information, while for others that don't have such an impact, we try to approximate their cost. And here's a very simple example. Again, using the example of the path latency, this node here can affect all of these dependents. So obviously its impact is very high, definitely higher than the red node, because it's only affecting one, right? And not only that, but if something changes in the top link here, the 4, then the green node can approximate what is going to happen in the rest of the nodes in the system, right? In the dependence. And this node can approximate what is going to happen here. However, the lower you are in this tree, of course you cannot figure out what is happening closer to your root. So in this case, we're actually broadcasting more frequently the nodes that are higher the cost of the nodes that are higher in this tree, and as we go lower, we reduce this broadcast rate. And we built this system. We have a prototype of export, and we have to, yes?
So how to optimize for different metrics? Like practically, you have all of them, they really conflict, right? Latency versus because if you just optimize the latency, everybody will be just one parent, right?
Okay, let me make something clear. You don't optimize at the same time for different metrics. The idea is that you can express different metrics, but every time you optimize for the specific metric you defined. So I'm not going to optimize.
So you mean the whole system? But then, like for latency, everybody will just have single parent and like a lot of children. Right?
It depends. If you have fan-out constraints, if you have bandwidth, consumption constraints, you're not going to do that.
So you don't optimize for metrics. You just have constraints.
You optimize for both of them. You have an optimization metric that can have certain constraints.
Okay.
So every time you
CPU utilization and, for example, latency.
Yes. And that will prevent everyone from connecting to the root and doing the processing at one single location at the root. If you have CPU...
but if I want to minimize CPU utilization and maximize minimize the latency.
We cannot optimize multiple, so you can express as a constraint, but not multimetric optimization here. Two applications. One is a multiplayer network game. Here we have a bunch of robots running around in an arena, and everyone expresses an area of interest, a square around them, and says, I want to receive the positions of the players that are actually inside this area. So what the game server will do is that it will push the positions of everyone in this game to the root of the tree, and then we're going to selectively send the positions only to the matching squares of interest. The second application, I have to admit, it's not so interesting. The demo got more attention in this case. It just simply disseminates RSS feeds. So in this case, clients say which RSS source we want to pull, and it's going to be sent to the root, and then we're only going to send the data to whoever is interested in that. This is easier to deploy, as you can imagine, so we deployed it on Planet Lab. And we measured, for example, the network latency that clients experience. And we want to compare with what would be the optimal in this case. If you only use network latency, then, as you just said, the best case is just directly go to the root and get the data. So this ends up being a star topology. And export starts with a random tree, and we can see that after a number of about 10 optimization steps, it can converge to the star topology. Okay. And this is a very easy thing, right? You don't really need export to tell you that this will be the ideal thing, so why would you use that? Well, in some cases, it's not so easy to figure out what is the optimal and just configure your network. So here's the case. Now, we're not only measuring network, but we're also measuring processing latency. So in the case of the star topology, the root will do all the work for us. We'll collect all the profiles, do the processing, the caching there, everything. While in the case of export, this is distributed across multiple nodes. Again, we start with a worse performance, as we did here. And at this point, we start actually fetching RSS feeds. And what happens is that we start collecting statistics on what is the actual processing time it takes to handle all of these queries. And you can see that the latency for the star topology is higher than what happens with export. And not only that, but once we start optimizing at this point here, we manage to improve further the performance. Why? Because we're able to figure out which areas of our network don't have too much processing load. So move trees that have high processing expectations, subtrees under this location. Okay. And now, the good news is that the state that we needed is very small. So during optimization, where nodes inside an optimization unit have to exchange information, what is your cost, how much will you change if I make this modification, things like that, it's only 700 bytes. And the maintenance state, to maintain all of this information, like what is my parent's latency, it's only 50 bytes. So that's very small. That's because of the aggregation functions. And here's for different metrics. So we measure bandwidth consumption, optimize for that, network latency, the bandwidth bottleneck in the system, how much data we're sending. And every time we try to optimize for that metric. This shows how much data I'm sending. The maintenance is sent every second, very, very small. And in this case, is optimization. The data I'm sending every time I'm trying to optimize. So this is data that are exchanged locally inside every unit. And you can see that it's pretty high for the latency, and that's because we're trying to optimize every unit. So every unit will try to improve that. While in the other cases, we can restrict what are the critical units that we have to focus on.
And the unit on this graph is bytes per second? It says bytes, but...
Oh, yes, but it is not per second, because this is per second because the maintenance, this is per optimization period. So this... So, unless there are any questions, I would like to, just briefly talk about the rest of them. Okay, I can go on. So, export can do very limited in terms of processing. We can answer queries like, give me the articles from CNN that have the word election. This is fine, but sometimes applications require higher expressivity, right? So we want to say, count for me the number of articles that appeared in the last hour and share the same title between CNN and BBC. So export couldn't do that. So we had to add stream processing operator capabilities in the system. So we have a language of stream processing operators we can use, and now we can express something like that, like a join between the two feeds and then a count within a window of 1 hour. And of course, now the servers can have stream processing capabilities, so whenever they get the data, they can actually perform the join and run these queries and send the results. Great. The other thing we want to do is be able to facilitate sharing across all of these profiles. You can imagine many cases where clients, they want to use the same processing up to some point, so they want to perform the same join and count, and then they want to answer their own use their own filters after that. So instead of actually placing that 3 times in a network, we want to be able to reuse some of this processing and just subscribe to it and get the filter, do the filter after. So the thing is that what would be the ideal architecture, network architecture for achieving something like that? So obviously we want to keep it tree-based. Why obviously? Well, because we have export, right? And it has some good benefits. It's generic, extensible, it can do well, so we want to reuse it. Could we have just used a single tree again? Well, if you want to be consistent with the semantics of this PubSub model, you would have to send every piece of information you want to share to the root and then send it probably through nodes that are not interested in that, through different locations where the processing is going to happen. So it's probably going to create a lot of redundant transmissions. So what we did instead used a network of multiple overlapping dissemination trees. And here's how the architecture works. We have this very simple stream processing query network. One RSS feed is going to be filtered, and then we're going to count the number of items. And we have an ABC feed that will have to be joined with the output of the filter. So everyone who wants to publish a stream simply connects to one node in the system. It's not the root, single root anymore, and just sends the data there. So, and everyone who wants to receive and process that subscribes to that. So we have now one tree that just sends this information, just this one RSS feed. Now the filter creates a stream as well, and it also publishes it. It creates a new dissemination tree, and everyone who wants to process simply connects and subscribes and gets the feed. Second tree. And now we have, you can imagine that the ABC will also be sent through a different tree, and everyone will just connect and get the data from that. And now the join that wants to get both of these feeds will simply have to subscribe and connect to 2 of these trees, right? So every node can connect to multiple trees depending on which streams it wants to receive. And conceptually, at least, these are different. Every stream is actually being sent through a different dissemination tree. So what this buys us is that we used again the publish subscribe model for now to decouple the operators. So now, in this case, every operator doesn't need to know about its upstream operators. This is completely decoupled, right? So it means that whenever I have to move this to another node in my system, I don't really have to notify my filter about this modification. I simply treat this change, this migration, as an unsubscription from the publish subscribe tree and a subscription of a different node. Right? And this allows us to be very adaptive to the number of modifications we can do in this query network. And not only that, but the fact that we have multiple dissemination trees that connect now nodes that are interested in the same content allows us to efficiently utilize the network resources and also to improve the bandwidth consumption of the system. And since we moved from a single tree architecture to a multi-tree one, we have to make some adjustments to maintain the good properties of export. So we have to extend our definition grammar. So now we have an extra aggregation model that aggregates the cost of multiple trees to give us the global improvement in the system. We have to measure, to express cost metrics for our operators and our queries. So we have a way of expressing what is the cost of an operator and aggregate that to define the cost of a whole query. And of course, we have to change the optimizations that we do. We cannot simply rely on network modifications. It has to be query-based changes. So we can migrate processing from one node to the other. We can replicate processing. So if we, for example, want to count over 2 streams, we can actually count independently in each one of these trees and then merge the results later. We can partition streams. So if we see that the tree and a root is getting too much information, we can actually split the input in 2 different dissemination trees. And the good thing is that now we have a system that can combine these different optimizations in one single framework without relying in a specific optimization metric. So periodically we can check, is it better to migrate or to replicate or to partition streams? So that's the novelty and the advantage of using something like that. And I'm not going to give details on how we implemented that, but feel free to ask me questions later. I want to focus on a very specific optimization issue that we had in both of these systems. So the principle was keep things as localized as possible. So again, here, if we have 2 dissemination trees and we have an operator here that relies on a node that connects to both trees. And now, if we want to migrate this processing and be consistent with these localized modifications, we just have to look in the close neighborhood that I'm aware of and only use this as the candidate locations. And this approach works well for certain metrics. So, for example, if I'm trying to improve the query response latency, we saw that we eventually end up moving things close to the sources, assuming that the selectivity of these operators is less than 1. So for certain additive and non-constrained metrics, we could converge close to the optimal. But the problem with all of these localized iterative optimization algorithms is that it's very easy to get stuck in a local optima. Of course, our system was not the exception to that. So very often we had a case like this. We want to improve the maximum processing latency. We have one operator that has very high load, and everyone around me has very small capacity. So I have nowhere to move this processing. So how do I get away from that? Well, ideally, I would want to find out which are the nodes that have enough processing to, even outside my local area, and just push the optimization there. So this is what we try to do. We introduce what we call directed optimization. We try to identify promising areas in our network that are not local, and we try to do it by creating a subscription service, a statistic subscription service that notify nodes of what is going on in other locations in the network. So here's a very simple example. I'm just showing one single tree. One tree disseminates this feed again. We've seen it many times. And now I'm focusing on latency. So every node knows of 2 values. It knows the value, the latency of its parent, right? And it measures the latency of this link here. So it knows how much time it takes me to reach my parent, and what is this my link latency. So what it wants to do is subscribe to every statistic that says, I have less latency than that. So we use this tree structure to create this statistic subscription service. So everyone sends its profiles, what sort of statistics it wants to create. Because we have a tree structure, we can aggregate these profiles again. And now the most generic of these subscriptions were actually going to be sent to the last branch. And the red filters here show what sort of information you should send upstream. So you should only send your statistics if it is less, if they satisfy this filter here. So now only this node will start adding its latency because it has a value of 23, less than 24. And the same goes on until we reach the root. And now statistics are sent downstream following the same filtering service. And we eliminate, of course, statistics that nobody is interested in. And now we have this node who suddenly realized that someone outside my area has better latency, so I can communicate and see if I can migrate my process there, or if I can optionally use this node as my parent. Okay. So we want to see how good this performs. And what we did is that we took the RSS processing dissemination system that we have and added some processing operators. And what we did is that we borrowed the Yahoo pipes, I don't know if I've used it, operators, where they provide a set of functions where you can manipulate and aggregate feeds. We implemented some of them operators and then ran experiments again on Planet Lab. So I'm just going to move on to the experiments. So in this case, we measure the bandwidth consumption, how much data we're consuming if we're sending data inside this multi-tree structure. We start with a random tree. So everyone who pushes their operators is going to be placed in a random node, and then we start optimizing. Here I'm showing the number of queries that we, yes?
What assumption are you making about the load distribution for the operators?
The load distribution?
Yeah. So, I mean, how bursty is the activity that is coming?
Okay, so we just had our own way of sending this update. So it was not really running on real time because you don't get updates on RSS feeds that often. So it was, I think, about 4 kilobytes per second that in average, that we were sending inside the network.
Okay. I mean, were the peak periods, much worse than in terms of the bandwidth?
We didn't have that. We didn't have that because it was more like inside. So we start with a random tree, and then we show we only use localized optimizations. And we saw that Xflow, by just using these local moves, it can converge to the optimal. So it can push the processing as close to the sources as the selectivity of the operators allowed us to do. And we also measured the query response latency. Again, random tree, this is the optimal, and without using any direct optimizations, just local moves, we eventually moved. Of course, you can see that now we increase the number of optimization steps, right? So it takes about 150 migrations to do that. So for additive non-constrained metrics, it was very easy to improve. And as I said, for others, it was not. So this is the case of maximum processing load. And here, Xflow just uses the localized. You see that it starts from a random tree, and then it stops improving very early. It cannot get close. It gets stuck in the local optima. While if we use the directed, we were actually surprised to see that we can eventually reach the optimal. And the optimal is not very easy to figure out in all of these cases. So if you have a metric that says improve the query response latency while keeping some load constraints, for example, someone asked me about that. Now we compare with a greedy, where the greedy, every time you assume global knowledge of your network, every time you add a query, you actually figure out what is the best placement. Okay? Again, we start with random, Xflow local, get stuck. There's nothing you can do, mainly because you don't know what are the constraints in other nodes, load constraints in other nodes outside your optimization area. While if you use the directed, you can improve even better than the greedy. So the direct optimization actually helped us escape from this local optima situation. So there is a lot of related work. I cannot even begin to describe what has been done in stream dissemination, distributed stream processing. The common thing across all of this is that they focus on very specific metrics. Now we have a system that it can express a variety of metrics and can do a pretty good job optimizing for that. There's of course work on making the construction of these overlay networks much easier, like the Macedon and peer projects. They don't focus on stream dissemination, and definitely they don't have stream processing functionality. So just to conclude, so my work focused on providing extensible overlays that can support the collection of streams, the processing, and the dissemination. We have a framework that you can express generic performance metrics and data types, and this makes the development of these applications much easier. And by relying on simple aggregations that are performed in multiple steps in the system, we were able to achieve some good properties. So we had optimizations that do not rely on the metric, but instead only on the aggregation semantics. We have a very lightweight impact evaluation model that can tell us when optimization is good or not. And we have ways of selectively disseminating statistics or approximating them. So the aggregation really helped us achieve all of this with very small costs. So, and no, thank you, just back up. So thank you.
So do you think it's possible to extend for multiple optimizations, like simultaneous? Just not optimize for latency or for processing, but have specify multiple constraints, like not constraints, but goals, and have a system which optimizes kind of to.
You would have to express some way the trade-off that
Yeah.
yes. It would be easy to have measure for different metrics and actually have the system evaluate the impact of these metrics. So easily you can go and say, do the measurement for bandwidth latency and for bandwidth consumption and link latency. And then when you do the optimization, you can actually see independently how you are affecting each one of them. Then what I would actually need is a way to tell me, which of the metrics I should pick, how I should, do the trade-off. So adding new metrics, it's easy to do. We actually had, I didn't show here, but we have examples where we use multiple multimetric overlay. Multimetric meaning that in the same function, I can express bandwidth times latency, for example, as my metric. Now, the trade-off, if you can express it like this, so bandwidth times latency, I can tell you which is going to be, if the modification is going to help this product or not.
So, okay, so if you can come up with a single criteria
yes.
optimization, then
if you give me the function,
okay.
I can do it. So the thing is that this system has these benefits of slow state if you express everything in this to aggregation level. So I have to be straight with that, right? So if you decline, if you don't follow these rules and if you don't follow the aggregation semantics, it would be hard for me to reduce the state that I have to maintain. So you can improve every metric, press every metric you want. Even you can, you don't have to rely on the sum, min, max. You can have every function. But if you don't give me, if I don't know enough about your function, it would be really hard for me to optimize the state that I have to maintain. I can handle many things. However, you have to follow the metric definition model to see the full benefits of the system.
So, join me in thanking Olga for talking.
Thank you.